Very good morning to all of you. Welcome you guys. Welcome you all. So how you are doing everybody? कैसे हो सभी लोग? I hope all of you are doing great. So let's start our discussions. Yeah, so this is the electromagnetics का plus course. The first class is on YouTube. The first class is on YouTube. All of you do join. All of you do join the session. All of you do like the session. All of you do like the session. चलो let's start our discussion. सबसे पहले, so here what we are going to discuss in this course. And this course we are going to discuss about the completely EC का syllabus. Remember this course we are discussing complete EC syllabus हम discuss करेगा. And EC का gate as well as ESC का. And this course is not for electrical gate के लिए. Electrical gate के लिए this course is not required. If any of you are electrical gate are there, so those fellows can leave the course. And but the electrical fellows, if you are preparing for the ESC, then this course is required. If the electrical fellows who are preparing for the ESC, for them in these two topics are required, that is electromagnetic waves and transmission line. These two topics are required for the electrical ESC के लिए भी. Okay, chalo, let's start our discussion now here, all of you. Let's start our discussion now here. So first, so let's enter into the electromagnetic waves. So we'll discuss about the basics of this electromagnetic waves. We'll briefly revise the Maxwell's equation first. First, we'll revise the Maxwell's equations. Okay, let's talk about the Maxwell's equation first. Let's briefly understand the four Maxwell's equation in detailed manner. And then we'll start the applications of the electromagnetic waves. Applications of the Maxwell's equations is nothing but electromagnetic waves only. Let's start now each and everything one by one. Chaliye. So, and all of you take your pen and copy. So, take the footer heading of Maxwell's equations. Maxwell's equations. Right, Maxwell's equations. The first one we'll talk about what tell me now Maxwell's equation. The first one, which is a Gauss law. Gauss law. Maxwell's equation, Gauss law. What the Gauss law is according to Gauss law, the net flux through any closed surface is equal to total charge enclosed. Total charge enclosed by the closed surface. The net flux, which is equal to total charge enclosed by the closed surface. The net flux, the electric flux will denote as psi, which will be equal to what we can say now here, the total charge enclosed by the closed surface. Net charge equal to total charge enclosed by the closed surface. This is Gauss law. Now this Gauss law, which we are modifying it as, so this is the flux, which is equal to, that is closed surface integral of d bar dot ds, that equal to what will be now Q enclosed. Charge in terms of charge density we can write. How will I charge in terms of charge density, in terms of volume charge density? That will be given as what we can say now, volume integration of rho v into dv. Volume integration of rho v into dv. What is this? Rho v is a volume charge density. How the volume charge density is defined as a basically, which is given as dq by dv. From that we can get the charge, which is equal to volume integral of rho v into dv. Now by equating the second term and fourth term, we are consider the second and fourth term. Now see what I will get, you tell me now. So this is closed surface integral of d bar dot ds, which is equal to what we can say now, volume integration of rho v into dv. Right. So the left side, what type of integration we have? We have a closed surface integral is there. So we are using the divergence theorem. So from divergence theorem, we'll convert this closed surface integral is converted to a volume integrations. Closed surface integral is converted to a volume integral. Closed surface integral of d bar dot ds, which is equal to what we can say now here. This is volume integral of del dot d into d. So from this we can write now here. So this is, we'll write it as a volume integral of del dot d, volume integral of del dot d into dv, and which is equal to what we can say, tell me now, volume integral of rho v into dv will do now, tell me now, rho v into dv. So here you tell me now this integral of volume integral. So both sides, left and right, we have same volume integrals now here. So from this, can I equate these two? Tell me now. Can I equate these functions now here? So from this, we'll get it as what you tell me now here. This is del dot d, which is equal to del dot d, which is equal to rho v. So this is the Maxwell's first equation. We know that relation between D and E. We know that D is equal to what you tell me now, epsilon naught into E na. We can place this one. So from this we can write it as what you tell me now, del dot of E. del dot of E, which is equal to what we can say, tell me now, rho V by epsilon naught. This is the first Maxwell's equation. This is called it as what, tell me now? This is the first Maxwell's equation. This is the first Maxwell's equation. Okay. We got this first Maxwell's equation we got. Now let's understand the physical meaning of this equation. The divergence means what, tell me now? Divergence means leaving nature, expanding nature, spreading nature. So here look at now divergence of the electric field, which we got something non-zero. Why it is non-zero? You see this thing here in case of divergence. If we have taken this point now, at this point if anything is leaving, then we can call that nature is called it as what, tell me now? Diverging nature. The field is diverging. This leaving nature, expanding nature, spreading nature is called it as a diverging nature. So here in this is the spread. This is in this case what we can say now here, divergence. Here we have the divergence of this vector. If I call this is a vector A bar, if I say the divergence of this vector at this location is what we can say now, positive. Right. Now if we have taken some other point, we have taken, let us say field is like this. So now at this point, what is the here? The field is coming and it is get nullified, right? And field is coming, it is get nullified. So in this case, what we can say now, this divergence is negative. Let me write, use it is the next page. We have the field. If we have taken some point, we have taken now here. Let us say the field lines are like this. Field means what, tell me now? It can be anything. Here we should talk about the electric and magnetic fields. We should talk now here. So at this location, field lines are coming and it is converging at this point, isn't it? So then in this case, what I can say now, divergence here. If I call this is the vector B bar, if I say, then means what I can say now, del dot of B, which is negative, isn't it? Now look at now here in this case. So divergence means basically what nature now here, leaving nature, spreading nature, expanding nature. If anything is leaving, we can say that that has a diverging field, leaving field, spreading field. Now that we are going to find out now here in this case, look at now. If we have taken a positive charge, we have taken, you see this thing here, positive charge. So how the electric field lines you tell me now for the positive charge like this now? Electric field lines like this for in case of a positive charge. All around the charges we have now. These are called as electric field lines, or we can say flux lines. These are the electric field lines. Right. So how this electric field lines or flux lines, you tell me now, this nature is what a living nature, spreading nature. So that's why in this case you tell me now here del dot E we have seen. Del dot E, which is equal to what you tell me now, rho V by epsilon naught, right? Rho V for this is the positive charge, rho V is positive only. So that's why at this location, how much the del dot E will come to be now here, which will be positive. So from this, see the electric field is what type of field, you tell me now? See the electric field is a diverging field. Electric field is what type of field? Is a diverging field. That's why divergence is something non-zero. Some value is there. But the nature of electric field lines are diverging nature, spreading nature. Okay. This thing clear now? Right, all of you do like the session. All of you do like the session. Next one. First thing we did. Now let's talk about the second law we are talking now here. That is the Faraday's law. Next one we are talking about the Faraday's law. According to Faraday's law. What is the Faraday's law here? The induced EMF in any closed loop is equal to time rate of change of its magnetic flux linkage. The Faraday's law. Yeah, you can see now here Faraday's law, that is the induced EMF in any closed loop. That's why the closed line integral of E bar dot dl closed loop is equal to what? Tell me now. The time rate of change of its magnetic flux linkage, that is d phi by dt. d phi by dt, where phi is the magnetic flux. Now we can write the magnetic flux phi is equal to, that is surface integral of b bar dot ds. Surface integral of what we can say now? B bar dot ds. Then here the EMF, it should be equal to what we can say now here? Closed line integral of, so that is E bar dot dl, and which is equal to minus of, we have d by dt of flux is equal to what? Tell me now. Surface integral of b bar dot ds. Okay. Now we are interchanging the integral and derivative now here. From this, we will get this EMF. It should be given as what? Tell me now here. Closed line integral of E bar dot dl, and which is equal to, interchanging this integral derivative now here, then it will become partial derivative, that is dou b by dou t dot ds. Dou b by dou t dot ds. Okay. Now I equating these two here. If I equate these two here, what we have? Tell me now. This is E bar dot dl, and which is equal to what? You tell me now here. This integral of minus dou b by dou t minus dou b by dou t dot ds. Now look at now here, in this case we can apply the Stokes theorem. From Stokes theorem, and what is the Stokes theorem? By using Stokes theorem, we'll convert the closed line integral is converted to a open surface integral. That is closed line integral of E bar dot dl. This is converted to what? You tell me now here. Open surface integral. Open surface integral of what? Tell me now. Del cross E dot ds. Now I'm equating them here. That is open surface integral of del cross E bar dot ds, which is equal to what? Tell me now here. Surface integral of minus dou b by dou t dot ds. Now tell me everybody. Right. Huh? So here both side we have same open surface integral. So from this can I equate the terms now here left and right. Can I equate the terms now here left and right terms now here by equating them? We can get the relation. What we'll get now here? So that is del cross E, and which is equal to what we can say, tell me now, minus dou B by dou T. Del cross E, which is equal to minus dou B by dou T na. This is the second Maxwell's equation we'll call. This is the second Maxwell's equation. This is the second Maxwell's equation. Right. Where B is what? Tell me now, magnetic field. So here we are taking the magnetic field is what type of? Here it is a time varying magnetic field. If B is not a variable, if it is constant, if B, if it is independent of time, tell me what happens. If it is independent of time, so then what happens now? This derivative will become zero now. The derivative will become zero. So that means will come to be what? Tell me now here, del cross E, which will becomes what? You tell me now, zero. So that means in this case what happens? You tell me now, this curl of the electric field is zero here, but here in this case curl of electric field is non-zero. Here what is this E is called as here? What is this E is called as? This E, which is called as what? Tell me now here. Dynamic electric field. This is called as what? Tell me now here. Dynamic electric field. And here this E is called as what type of electric field? Is a static electric field. Static electric field. In case of a dynamic electric field, which is non-zero, but static electric field case is zero. From this, what we can comment? You tell me now here. What we can comment now from this now here? Static electric field is irrotational. Remember, static electric field. Electric field is irrotational. But dynamic electric field is dynamic electric field is rotational. Yes, this point you understood now? Why rotational? Why rotational? Hmm? Right. Next one. The third one. Third thing we got from the Ampere's law. That is called as Ampere's Maxwell's equation, which they call. Ampere's Maxwell's law. So according to this Ampere's Maxwell's law, so this is this closed line integral of h bar dot dl, which is equal to I that is equal to, we have, this is the surface integral of, what you tell me now here, j plus dou d by dou t, j plus dou d by dou t dot ds. Okay, where did j? So by equating the first and last terms, then we can write it as, what, tell me now here, closed line integral of h bar dot dl, and which is equal to open surface integral of j plus dou d by dou t dot ds. Now we are writing it as a closed line integral. Right side we have open surface integral. We are applying a Stokes theorem. We are applying a Stokes theorem. By using Stokes theorem, what we can do? We'll convert this closed line integral to a open surface integral. Right. So then, which will come to be a, what, tell me now here, the surface integral of del cross h dot ds, and which is equal to, what you tell me now here, this is surface integral of j plus dou d by dou t dot ds. Right. So from this, we are equating the corresponding functions now here. That is del cross h, which is equal to, what you tell me now here, j plus dou d by dou t. Right. So this is the third Maxwell's equation. This is called as, what, tell me now, third Maxwell's equation. Right. This is the third Maxwell's equation. Del cross h is equal to j plus dou d by dou t. Where what the j is called it as a j, which is equal to, what you tell me now, the networks you will study this thing. J is equal to sigma E, Ohm's law. So this is where j is called it as a conduction current density. Is called it as, what, tell me now, conduction current density. Conduction current density. Right. So here the second term we'll take it as JD, which is, what, tell me now, dou d by dou t. And the second term, this is called it as a displacement current density. Displacement current density. The second term, this is called as, what, tell me now, displacement current density. Okay. Second term, this is the displacement current density. Now we can write it as, what, tell me now here, displacement current density, conduction current density. How we can get the current from current density? By integrations. Then we can write it as integral of, so we can do it as, what, tell me now, j plus, this is, what, tell me now, dou d by dou t dot ds. Right. So this term, first term will use a conduction current, second term will use a displacement current. The total current which is given as combination of conduction current as well as a displacement current only. Total current is a combination of conduction current and the displacement current. Right. Done? Next one, the fourth equation, and this is called as a Gauss law for magnetic field. This is called as a Gauss law for magnetic field. Gauss law for magnetic fields. And Gauss law for magnetic field, which will be given as this is closed surface integral of b bar dot ds. Closed surface integral of b bar dot ds, which is equal to 0. Closed surface integral of b bar dot ds equal to 0. By applying a divergence theorem, we'll get the equation as what you tell me now, del dot b equal to 0. This is called it as a Maxwell's fourth equation. This is the fourth Maxwell's equation. And what is the significance of this equation? This significance, it will indicate that how the magnetic lines, you tell me now, magnetic lines are always in a closed loops. This equation signifies that what, tell me, magnetic lines are always in a closed loops. Yes, so how we have a magnetic lines are, if we have conductor, if there is a flow of current through the conductor, how we have a magnetic lines, you tell me now? The magnetic lines are like this. The magnetic lines, which could be like this, which will move always in a closed loops like this. These are the magnetic lines. Magnetic lines are always in a closed loops only. And this equation also signifies that magnetic monocharges does not exist. Magnetic monocharges. Monocharges means monopoles. Monocharges does not exist. And this also signifies that magnetic lines have neither source nor sink. Neither source nor sink. Okay. Done? Yeah. Right. There are the four Maxwell's equation we got. Now let's see the things now. So look at now here the four Maxwell's equations. What the equation we have? Tell me now, fourth equation. That is the del dot B, which is equal to 0. So here look at now here. Del dot B is equal to 0. The divergence of a vector is 0. If the divergence of vector is 0, then what we can write now? Then what we can call this vector is a solenoidal vector. So that's why this magnetic field is called as what type of field is a solenoidal. Magnetic field is a solenoidal field. Any solenoidal vector can be expressed as Any solenoidal vector can be expressed as the curl of some other vector. Okay. Any solenoidal vector can be expressed as curl of some other vector. Here B is a magnetic field. Magnetic field is a solenoidal field. So that's why what I can do, this solenoidal field we can express as curl of some other vector. That is what you tell me now. We can say this vector B bar. We can write it as a curl of some other vector. We can write that vector as A. Right here, what is the B you tell me now here? With B is a magnetic flux density. If B is a magnetic flux density, then this A is called as a magnetic vector potential. Is called as what you tell me now? Magnetic vector potential. Magnetic vector potential. So where A is called it as what, tell me now? Magnetic vector potential. Right. Next. Now we have vector potential. Now we need to develop the scalar potential also. Scalar potential. Let's see how we'll develop the scalar potential. So we have the relation now here del cross E. Del cross E, which is equal to what, tell me now? Minus dou B by dou T. Del cross E, which is equal to what, tell me now? Minus dou B by dou T, right? And here, as we have seen now, B is equal to what, you tell me now? B is equal to, in terms of magnetic vector potential, we can write this as del cross A. We'll place then here. Then we'll get it as del cross E, which is equal to minus of dou by dou T of what, tell me now here? Del cross A, we can place it now. So this is del cross E, which is equal to what, tell me now here? This is minus del cross of, we can say this as dou A by dou T. If I bring to this side, so it will come to be a del cross of what, tell me now here? E plus what we can say now, dou A by dou T. Yes, equal to 0 na? Right. So look at now here. Earlier in case of a static fields, we have seen for static fields, what happens, you tell me now? Del cross E, which is equal to 0, static field. So that's why we wrote this as E, we expressed as E is equal to minus del with the relation we have seen. Right. But here, in this case, del cross of this term 0 na. So that means what I can write now here, this is any irrotational vector can be expressed as what, tell me now? Any irrotational vector. Any irrotational vector can be expressed as what, you tell me now? Gradient of some other scalar function, some other scalar. Right, here also the same property we write now here. So that is E plus what I can say now here, dou A by dou T, and this which we can write it as minus del V, tell me now, and which is equal to minus del V now, all of you. Fine. So from this, what we can write to, tell me now, E is equal to how much now? E is equal to, that is minus del V minus dou A by dou T. Right. Minus del V minus dou A by dou T. Where what is the V is the? V the scalar potential. V is called as scalar potential. And A is called as what element of vector potential. This is the relation. Okay. This is the relation for the scalar potential and vector potential. Done. The other things what you should know here is about the boundary conditions. The other thing you should know about it is what you tell me now, the boundary conditions you should have. Let's talk about these boundary conditions also. And what the boundary conditions? We have totally 4 boundary conditions are there. So 2 for electric field and 2 for magnetic fields. What the first boundary condition now here? That is E1t, which is equal to E2t. That is what, tell me now, tangential components of electric field intensities are continuous. Tangential components of electric field intensities are always continuous. And the second boundary condition is what you tell me now, D2n minus D1n, which is equal to rho s. D2n minus D1n is equal to rho s. And the third boundary condition is, that is H2t minus H1t, which is equal to K cross En cap, where what the K is called it as a surface current density. K is called as a surface current density. K is a surface current density and with the units of amperes per meter. And what this En cap is a unit normal vector. En cap is a unit normal vector. And keep in mind this should be taken from medium 1 to medium 2, keep in mind. This should be taken from medium 1 to medium 2, we have to move, keep in mind. Then only this formula. Some textbook they will follow from medium 2 to medium 1. In those cases they will write it as what, tell me now here, An cross K, they will ulta, they will write. Okay. Here we are following from medium 2 to medium 1, medium 1 to medium 2 we are following. And the fourth boundary condition is B2n is equal to B1n. B2n is equal to B1n. These are the boundary conditions. Right. So finally we have the 4 Maxwell's equations and 4 boundary conditions. And what are the Maxwell's equations? Recollect it now once all of you. What are the Maxwell's equations we have? Tell me now. The first Maxwell's equation is what you tell me now here. So that is del dot D, which is equal to rho V. And the second one, that is what you tell me now, del cross E, which is equal to what? Tell me now, minus dou B by dou T. And the third equation is what? Tell me now, del cross H, which will be equal to J plus dou D by dou T. Next, the fourth equation is del dot B equal to 0. These are the four Maxwell's equations. These are the equations you have to remember at any cost throughout our subject. So we'll focus is about these equations only. Any problem arises, so we'll come to here these equations only. And each and every formula has been developed from these four equations only. And the other relations, what we can do here, the constitute relations we have. What is the constitute relations are? We have, these are, we have, that is D is equal to what you tell me now, epsilon naught E. And that is B is equal to what you tell me now here, this is mu naught H. And J is equal to what? Tell me now, sigma E. J is equal to sigma E. These are called as a constitute equations. Constitutive equations. Okay. Some questions, though here still we are not at reached to questions discussion level. Still we are in the theory only. So here we have so much of theory is baki is there. So after completion of theory, we'll start problems. Right. So here, so you have to remember this four Maxwell's equation, the constitutive relations. Throughout our discussion, our focus is about these equations only, everywhere. Done. Yes. Fine. Okay, yeah, that's it for today's class. I hope आज का सेशन में आप सभी को मजा आया होगा. The same manner will continue the remaining classes also. Do try to be follow the classes regularly. All of you do like the session first of all. All of you do like the session, everybody. Try to follow the classes same manner, regular manner. So to have this great learning experience. So I will try to discuss each and everything in detailed manner. Do follow the same manner. ठीक है? Yeah. चलो. Okay then. See you. Bye.